Hello there, and welcome to the second half of the story of Pythagoras and all of his Pythagorean buddies. Last time we left off on a little bit of a cliffhanger, and I hope it didn't drive you too crazy, because today we're going to figure out what this mystery was all about. Although, if it did drive you a little crazy, don't worry, you're in good company. At the end of this story, Pythagoras goes insane. Spoiler, sorry. All right, what was the mystery here? What was the cliffhanger? The cliffhanger was this question. Pythagoras went to Egypt. He saw the 3, 4, 5 rope. He saw that 3, 4, 5 makes a right triangle every time. And then he wondered, since he was super into numbers, he loved different ratios and different harmonious number combinations. In fact, he and the Pythagoreans thought that harmonious number combinations were really special. In fact, they might even be magical or divine. So they were obsessed with this idea of, are there other combinations of numbers that work to make a right triangle? And they found that most combinations didn't work, but every once in a while, as they were testing things, they stumbled upon combinations that did make a right triangle. So the real question here, the big mystery is, why do the combos that don't work not work? And why do the combos that work, work? And eventually, Pythagoras and the Pythagoreans figured out the answer to that question. Now, I will say that we don't want to be Eurocentric here. We have some evidence to suggest that there were people in other countries or cultures around the world who had kind of figured this out, maybe much earlier than Pythagoras and the Pythagoreans did. But once he and his buddies figured this out, this information and news kind of spread like wildfire, and it really changed the whole world of math in the Western world at that time. So what was the mystery? What was the mystery? Well, let's take a closer look at these numbers. And let's go with the 3, 4, 5 combo that we know makes a right triangle. And here's the answer to why this works. We know about exponents. So if I said, what's 3 squared? You know that that means 3 times 3. If I said, what's 4 squared? You know what that is. That's 4 times 4, which is 16. You know what 5 squared is. That's 5 times 5, which is 25. For these combinations that do make right triangles, watch what is true. Dum-da-da-da-dum. That is the answer to this whole mystery about why some number combinations work to make a right triangle and some combinations don't make a right triangle. If the numbers make a right triangle, then one leg squared plus the other leg squared will equal the hypotenuse squared. And I'll just show you real quick that that's why 5, 12, 13 works as well. 5 squared is 25, plus 12 squared is 144. And what's 25 plus 144? 169. And guess what? 169 is 13 squared. And that's why 5, 12, 13 makes a right triangle. And you can test that on 11, 60, 61. You can test that on 13, 84, 85, if you want to bust out your calculator and try those numbers. And in fact, you could even test this on these ones that didn't work, and you can find out why they didn't work. What's 1 squared? 1. What's 2 squared? 4. What's 1 plus 4? 5. Is 5 3 squared? No. So the Pythagoreans finally had an answer for why do some number combinations make a right triangle and why do some number combinations not make a right triangle. And you might be thinking to yourself, this doesn't seem like that big of a deal. But I'm going to show you how this can become really, really useful and important, not only just in math, but in life in general as well. Let's go ahead and summarize what we've just learned. The Pythagoreans noticed a strange relationship between the three sides of a right triangle. Any right triangle, no matter whether it was long and skinny, no matter whether it was kind of square-ish, no matter whether it was turned or rotated, any right triangle has this relationship. The sum of the squares of the legs always equals the square of the hypotenuse. In other words, this number squared plus this number squared will equal this number squared. This number squared plus this number squared will equal that number squared. And if it doesn't, then that's not a right angle right there. And if that is a right angle, then this squared plus this squared will equal that squared every time. And the Pythagoreans tested this and tested this. And for the last 2,500 years, we've been testing it, and it works every single time. Leg squared plus leg squared always equals hypotenuse squared in a right triangle every time without fail. So this is one of the most important equations in the history of mathematics. Leg squared plus leg squared equals hypotenuse squared. What we do with this equation is we abbreviate it as a squared plus b squared equals c squared, because that's just a lot easier to say. And this equation is what we now call the Pythagorean theorem. You might have heard that phrase before, and now you know what it means. The Pythagorean theorem is an equation, and it's an equation that states for every right triangle in the universe, the leg squared plus the other leg squared will equal the hypotenuse squared every single time. So we use the letters A and B to represent the legs, and we use the letter C to represent the hypotenuse. By the way, I'm going to back up just one moment here and look at this little picture of Pythagoras. Maybe you want to pause the video and see if you can see the Pythagorean theorem hidden somewhere in that picture if you look really, really closely. A squared plus b squared equals c squared. Leg squared plus leg squared equals hypotenuse squared. Okay, so that is the Pythagorean theorem. A squared plus b squared equals c squared. Now let's talk about what you're going to have to do with the Pythagorean theorem. You're going to have to take a triangle and you're going to have to answer, is this a right triangle? It looks like a right triangle. That looks like 90 degrees. But is it exactly 90 degrees? Do we know for sure that this is a right triangle? Well, with this one, we already kind of know the answer because we already did say that 5 squared plus 12 squared does equal 13 squared. We showed that 25 plus 144 equals 13 squared. And so that means, is this a right triangle? Yes. That is definitely perpendicular, right angle, perfectly upright leg. So the Egyptians could have used a 5, 12, 13 rope if they wanted to. It's just that a 3, 4, 5 rope is a little bit easier. Okay, good. Now, we can use the Pythagorean to test if a triangle is a right triangle or not, or we can take a triangle that we know is a right triangle. We can take a right triangle that we know is a right triangle, and now that we know the Pythagorean theorem, we can solve for missing pieces. Okay, so what does x equal? If you think you can figure this out, go ahead and pause this video right now. And if you can't figure this out, here's how you would do this. You would set up this equation, a squared, b squared, c squared, leg squared, hypotenuse squared, and just put these values in to that formula. So the two legs are 12 and 16. So we're going to do 12 squared plus 16 squared equals, what's the hypotenuse? We don't know. So I'm going to put an x right there. And can you solve this equation? I think you can. This is 144. Grab your calculator. You can see that this is 256. And we still don't know what x squared is or what x is. But we can add these together. We get 400. And now we just have to figure out a number that when you square it makes 400. Well, basically we're going to unsquare the 400, right? And what's that going to give us? That's going to give us x equals 20. And we just solved a right triangle by using the Pythagorean theorem. What's the Pythagorean theorem? A squared plus b squared equals c squared. Leg squared plus leg squared equals hypotenuse squared. And then just look, does it seem like that could be about 20? Yeah, 12, 16, seems about right. Okay, so let's try another problem. Let's see about a square. Wait a second. What does a square have to do with the Pythagorean theorem? I thought the Pythagorean theorem was about triangles. Well, we can take a square, let's say it's 1 foot by 1 foot, and turn it into a triangle. Can you imagine just folding it in half or just cutting it in half? Guess what you would have? Not just any kind of a triangle, but a right triangle, because we know that's a right angle right there if this was a square. Now, what if I asked you, what is the length of that diagonal that's going corner to corner on this square? Now, we can use the Pythagorean theorem to find that number because 1 squared plus 1 squared should equal x squared, right? Now watch what's going to happen on this problem. When I do 1 squared plus 1 squared equals x squared, something interesting happens. What's 1 squared? What's 1 squared? Okay, this is really easy. What's the problem? The problem is I don't know any number that makes 2 when you square it. What times itself makes 2? Uh-oh. You can't really unsquare a 2, can you? Well, you can punch it into your calculator and get an estimate of what the square root of 2 equals. But we know that that kind of a number is called what kind of a number? That's called an irrational number. And the problem with irrational numbers is they're decimal thingies that go on and on and on and on forever. And they're called irrational precisely because you can't make them into a ratio. They're irrational. This is where the story turns dark for Pythagoras. He believed in the harmony of great number ratios. In fact, they made beautiful music by making string lengths with ratios. And he liked those Pythagorean combinations of 3 numbers that worked harmoniously together. And the problem with the square root of 2 is it's not rational. It doesn't work harmoniously in the known number world. It's kind of icky and messy. And Pythagoras didn't believe that numbers could be that way. He loved numbers. He even worshipped numbers, maybe, right? And so when one of his Pythagorean buddies showed him that in fact there are such things in the world as irrational numbers, Pythagoras did not react well. He kind of lost it. And depending on what historical sources you read, he either just completely went insane, or he took that Pythagorean buddy who proved this to him and threw him off the side of a boat and killed him, or he might have even killed himself. But one way or another, this is actually kind of a dark story, and it's sad that Pythagoras couldn't adapt to this new information, but unfortunately, the reality of our existence is there are numbers in the world that are irrational, and we're just going to have to deal with it because we don't want to lose our minds like Pythagoras did. So sometimes when you use the Pythagorean theorem to solve problems, you get nice numbers. Sometimes you don't get nice numbers. That's just the nature of the reality that we live in. All right, one more example problem. Let's say you had this right triangle, and I'll tell you, it is a right triangle. And let's say I asked you to solve for x. On this one, you're going to have to be careful. And the reason you're going to have to be careful about this one is, which of those 3 sides is the hypotenuse? When you put your x and your 12 and your 16 into this formula, where is the x going to go, where is the 12 going to go, and where's the 16 going to go? The right angle is here. Hopefully you can see that. That's definitely not a right angle. That's definitely not a right angle. So that means that x and 12 are the legs. and that means 16 is the hypotenuse. So when you set this up, what are we going to put in for A and B? We're going to put x, come on, work with me here. We're going to put x is one of our legs, 12 is the other one of our legs, so it's going to be x squared plus 12 squared equals the hypotenuse squared, that's the 16. Another clue on this is, remember, the hypotenuse is always the longest of the three sides, so it's got to be 16 in that C slot. Now to solve this equation, okay, we've got x squared, 144, and we already had these same three numbers, right? So we knew that that was 256. In order to get x, you're going to have to do something different. You're going to now have to subtract a little bit to get x by itself. And if you take away 144 from the left, you've got to take away 144 from the right to keep it balanced. And now we're going to have, let's see, 2, 1, 112. And do you think that's going to come out rational or irrational? X is going to be the square root of 112, and that's irrational as well. That's okay, it doesn't mean you did anything wrong. The main point of this example problem is, be careful, the x doesn't always go here, the hypotenuse always goes there. So be careful about what piece you put into what slot, and if you're solving for a leg and not a hypotenuse, you're going to have to do a little subtraction before you square root. Okay, that's the Pythagorean theorem, and that's how you're going to use it to test triangles to see if they are right triangles, and to also solve for missing pieces of right triangles. We will talk soon about why this is important in real life and why right triangles are such important shapes in the world that we live in. But for now, you just need to know what we call the good old Pythagorean theorem. And the Pythagorean theorem is that a leg squared plus a leg squared always equals the hypotenuse squared in a right triangle. The Pythagorean theorem. It's a beautiful thing. All right. Thanks for listening. Thanks for watching. I hope you enjoyed and learned something today, and I will see you next time.